So there's one general comparison results, and as I said, this now refers to just projection value measurements. So when you allow general POBMs, that is, also allow yes/no measurements to be positive operators, then actually because of this effect of noise in the measurement that counterbalances, you don't expect a clear inequality. Right? So now we definitely restrict to projection value. And actually in that case, there is available a way to quantify the deviations, the errors, that doesn't even need the transport distance. It still uses the same elements, that is a metric outcome space and an error exponent. But it doesn't actually need this whole idea of transport. So this we call the calibration error. So this is a projection value measurement. And A prime is an approximate A. So it has the same outcome space. That's the only, but this doesn't have to be projection value. And of course, typically it's not going to be, right? So if you make an approximate position measurement and have added noise in that, for example, then this is not going to be projection valued. So only the reference has to be projection valued. Okay, so in that case, actually, so then there are states with sharp A. Remember, we are testing all these devices on various states. Now, one way to do that is to say, okay, let's take a state where I know the value of A, of this reference measurement. I know this has a sharp distribution. There's a particular kind of preparation, and so I know what a good measurement should give, namely that value, right? Because the reference observable gives that every time, or very nearly. Right? Then on those states I test A prime, and then I typically get a distribution which is broader. And so but then I can look at the deviation of that distribution from the value I know it should have. So actually we can do something like this. So the calibration distance between A and A prime is this largest distance I get of the output distribution. Now that was again the delta now for the transport distance, but I'm taking the transport distance with respect to a pure state. It's the output distribution of the approximate measurement, and you look at its distance from a certain value in the outcome set. The corresponding point measure, right? And you do this for all states. So it's a supremum over states and these values. And the condition on the states is that the distance with respect to the reference, right? So if you measure the reference observable on that state, you get delta A with very high precision. So let's say this is less than epsilon. Now this quantity will depend on epsilon, right? But actually, if you have discrete observables, so you could actually make this epsilon equal to 0. For a position measurement, you couldn't, because there's no state that has zero variance in the Hilbert space. But so just say this is very sharp, right? And then you can see from the structure of the supremum, if I increase the epsilon, the number of states that I take the supremum over becomes smaller, so the number becomes smaller. And so delta C of A and A prime is just the limit as epsilon goes to 0 of these guys. So you see how the projection valuedness goes in? Such states don't exist for general POBMs. So we need them in so that this supremum doesn't become empty for small epsilon. Right? So of course for projection value that is guaranteed. Okay, so this is the calibration error. Now it's very clear that the calibration error is is smaller than the distance of the observables that are defined before, simply because you're taking this supremum over a smaller set of states, right? So only those that are sharp. Actually, you could also throw in convex combinations of states with sharp distribution. That wouldn't change this quantity. So anyway, this is a straightforward inequality, and that would be like the standard measurement. This is used in the standard measurement uncertainty. But then we have, in the projection valued case, we have this additional thing that lies between the two. Okay. So let me state this. This I need to state our general result. So the result is this. So it's a theorem. So given projection valued observables in a finite dimensional Hilbert space. Well, there should be A, problem A and B. Um, then, so let me start with the loose statement, right? So the preparation uncertainty is smaller than the calibration. That's the new one that I just defined. And this is less than the measurement uncertainty. That I just explained, right? You have scare quotes in this statement of the theorem. It's not a theorem as stated, because preparation uncertainty isn't just a number. We're not just comparing number. We're actually comparing patches in a diagram. So the precise statement in the uncertainty diagram, and for each of these we can do that, right? We just write down the corresponding pairs corresponding to states, corresponding to joint measurements judged by calibration uncertainty, and the same thing for the measurement uncertainties. So in the uncertainty diagrams, the convex hull of the preparation uncertainty region is actually the biggest of these. Is larger than the C calibration uncertainty region, and because these quantities are smaller, so this is larger than the MU region. Okay, some things are strange about this result, and I'm not completely happy about it. One is the convex hull here. It comes in due to our technique of proof, by which we compare linear bounds on these regions, and so automatically we look at the convex hull of this region. Actually, because variances are not convex functions, it's not automatically clear that, well, actually in general, the preparation uncertainty region, that the set of pairs that you get in this way, doesn't have to be convex. So that's definitely true. And we also know, I'll give you an example in a sec, that this inclusion actually may fail. So it's partly, we understand why the convex hull comes in from the method of proof, but also if we leave it out, the theorem is no longer true. That's one strange thing. The other strange thing is the finite dimensionality. Now, if you know my work, you will be surprised that I do something in finite dimension where the concepts that are here are clearly valid in infinite dimension. And you would think that by some kind of approximation argument, you could just make it go there. Right? Just extend it to infinite dimension. I can only say I would certainly have done that if I had seen a way, but that doesn't seem to be so easy. So there's actually some subtleties left here that might be quite interesting. Technically, what we're using about the finite dimensionality is that the identity of, there's something like an equidistribution. So the identity operator, properly normalized, is a density operator. It's trace class. And that is, of course, not true in infinite dimension, but we are making use of it in the proof. So this is how this goes in. And in this case, we don't have counterexamples. Okay, so let me just wrap up by showing you a diagram in a simple finite dimensional case, few outcomes, where you can see exactly these inclusions. Also that what I said about the convexity and the necessity of the convex hull. So the example that I brought, where we worked this out in detail, is actually a three-dimensional Hilbert space. The observables are the two angular momentum components of the spin 1 representation. Those are A and B now. The metric in the space of outcomes, the outcomes now are -1, 0, and 1. And we just take the distance of these numbers, right? So that's the metric. And the error exponent is 2, right? So that gives a diagram like this. And so preparation uncertainty, as you can see, I mean, this slightly darker line here indicates the actual preparation uncertainty region. The convex hull is the fat red line. That's a bit larger, actually, right? So it has, as I told you, it doesn't have to be convex. Then we have the calibration uncertainty region and the measurement uncertainty region in blue, right? So as you can see here, first of all, the claim that I made here is clear, right? So the red curve is below the green curve is below the blue curve, right? That's this stuff. So actually, these don't actually have to be the same, right? You're actually taking a different supremum. And it depends on context. Which of these you would like to choose to express measurement uncertainty? I mean, they're both of the same. They're both of the measurement uncertainty kind. They refer to the possibility of making a good joint measurement. Just the criterion is a little bit different. But what you also see is that the preparation uncertainty region without the convex hull is actually going a little bit above the calibration uncertainty in one point, right? So if we forget the convex hull in the statement that I gave, then actually we get a wrong theorem. Now, the numerics of this is not, well, we had to work a little bit for that. For preparation uncertainty, this is computing variances, is relatively simple to do that. For the measurement uncertainty, we had to devise semi-definite programs, use some of the Cantor-Roberts duality for efficiently evaluating the transport distances. But that can be done, right? You can reduce that. You can use the duality to reduce it to finitely many cases, and those you can solve with semi-definite programming. That's the numerical technique that you see here, and this is just the outcome of one such run. Okay, so indeed we have this general kind of inequality. How general it actually is when we allow infinite dimension, we don't really know. But at least this will cover a lot of the cases that would be of interest in quantum information theory, and that closes my series.